Welcome to a second lesson on graphing trig functions. In the previous lesson we looked at how we could graph sine and cosine, including all their transformations. And in this lesson we're just going to look at the basics of graphing the other functions, so tangent, cotangent, secant, and cosecant. So our main goal, again, is to be able to recognize what those graphs look like, to be able to sketch them maybe if we need to. And then to be able to identify their domains and ranges for each of these four functions. And again, the overall process is we're going to look at how we can extend what these functions represent in terms of the unit circle, and what they would look like then as an algebraic function. So we want to graph our tangent function. We're thinking of graphing f of x is equal to the tangent of x. We could get at doing this by remembering that tangent is the same thing as sine over cosine. So let's compute sine and cosine at various values, and then we can go ahead and compute tangent and plot our points and see what the graph looks like. So I'm going to kind of run through a lot of the computations here. I'm not going to go through explicitly step by step how I get these, but you can go back and look at the unit circle and how we can use the unit circle to compute all these. So to compute these, let's just quickly kind of set up a unit circle. If we started at 0 and we're going to start with a negative pi over 2, that means we're going to rotate in the negative clockwise direction to negative pi over 2. And the coordinate there is 0, negative 1. We're then going to look at a negative pi over 4, which is the 45-degree angle. We're going to look at 0, which is the coordinate 1, 0. And then we're going to rotate through pi over 4 and then up to pi over 2, which is the point 0, 1. Okay, so negative pi over 2, the y-coordinate is a negative 1. Negative pi over 4 would be a negative root 2 over 2. 0 would be 0 because that's the y-coordinate. Pi over 4 would be root 2 over 2. And then pi over 2 would be a positive 1. So those are the x-coordinates, or those are the sine values that we get at those values. For cosine, again, remember cosine is x. So cosine at a negative pi over 2 is 0. It's then going to be a positive root 2 over 2. It's going to be a 1. It's going to be another root 2 over 2. And then it's going to go back to 0. So to compute our tangent, remember we're doing sine over cosine. So we're going to take negative 1 divided by 0, and unfortunately that doesn't exist. If we take a negative root 2 over 2 divided by a positive root 2 over 2, we get a negative 1. If we take 0 divided by 1, we get 0. If we take a positive root 2 over 2 divided by another positive root 2 over 2, we get a positive 1. And then 1 divided by 0, again, is undefined. It doesn't exist. So we can go ahead and plot some of these points. We know that at negative 1, we have, at a negative, so each of the vertical lines here is a distance of pi over 2, so each one is pi over 4. So at a negative pi over 2, so negative pi over 2, we have a negative 1. At a negative pi over 4, so now we can go ahead and plot these points. We need to use the x values of a negative pi over 2 up through a positive pi over 2. And the way I've set up the grid here is each vertical line represents a distance of pi over 4, because 2 of them are pi over 2, so one of them would be pi over 4. So we're going to start over here at a negative pi over 2. Well, unfortunately at negative pi over 2 there's nothing. It doesn't exist. So let's move on to the negative pi over 4. At negative pi over 4 we have a negative 1. At 0, so when x is 0, tangent is 0. And then when x is pi over 4, tangent is 1. And then at pi over 2, again, we get does not exist. So what does the undefined parts of the graph do? If you think back into your algebra class, when we graphed rational functions, what happened when we had a 0 in the denominator? What happened if that function was undefined? And what, if you remember, we ended up getting something called a vertical asymptote, which is a vertical line that the graph approaches but never touches. So in this case, we're going to have a vertical asymptote at a negative pi over 2, and another one at a positive pi over 2. So the graph, it has to go from negative infinity through these points and then up through positive infinity. Okay? And so that's what the graph of tangent is going to look like. Now that's just one part of it. If you remember, again, with the circle we can go around and around and around forever in either direction. Anything else we do on this, the tangent graph will always look the same. So this here is one period. That's our standard period. That's going from negative pi over 2 to a positive pi over 2. So if you go from a negative half to a positive half, that means your period is pi. Okay, that's our standard period. And anything else is just going to be a repeat of that. So if we know what that first piece looks like, we know what everything else is going to look like. So the graph is just going to continue doing this forever and ever. Okay, so as long as we know this first piece, and it'll do it to the left, as long as we know that first piece, we can always graph our function. Okay, so that's what our tangent graph looks like. Now to try and again summarize some of this, again we know that the period, the standard period is pi, and that occurs between a negative pi over 2 and a positive pi over 2. And we're going to have a place where the graph is undefined, where we have a vertical asymptote at every odd pi over 2. And so this expression here, pi over 2 plus pi k, is just a way of saying all the odd pi over 2s. Okay, it's all the odd pi's over 2. So like 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so forth. And we can go in the negative direction as well. And so what that means too, whether or not we shift the graph to the left or to the right, any distance of pi, so any multiple of pi really, we're always going to end up with the exact same graph. So it's just a carbon copy of itself, just moving to the left and to the right. All right, let's do the same thing with cosecant. So remember cosecant, cosecant is just 1 over sine. So if we can find values for sine, we can find what cosecant is going to look like. And again, I'm just going to kind of run through here real quick. The sine at 0 is 0. The sine at pi over 2 is 1. Sine at pi is 0. At 3 pi over 2, it's a negative 1. And at 2 pi, it's 0. And again, that just comes off the unit circle. So to do cosecant, I need to take 1 and divide it by each of these. So 1 divided by 0 is undefined. It doesn't exist. 1 divided by 1 is 1. By 0 again does not exist. We get a negative 1, and then again it's undefined. So at each of these undefineds, because we're dividing by 0, we're going to have a vertical asymptote. So we're going to have asymptotes at 0, pi, 2 pi, and if you follow the process, it's going to be 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, same thing in the other direction as well. So negative pi, negative 2 pi, negative 3 pi, and so forth. Okay. So if we start, so the only points I actually can put on here is at pi over 2 we have a 1, and at 3 pi over 2 I have a negative 1. And notice these are on the maximums and minimums of the sine graph. In the original sine graph, we talked about this in the previous lesson, its normal period goes from 0 to 2 pi. Same thing is going to happen here because it's just reciprocal. Now, as sine gets smaller, what happens if you take 1 over something really small? It gets really big. So what happens is that our cosecant graph is going to look something kind of like this. It's not actually a parabola, but it kind of looks like a parabola. Okay, because it doesn't open up forever. It continues. It's stuck within the two vertical asymptotes. So the graph of cosecant for one period has this sort of upward curve and then this downwards curve, and anything else is just a copy of this part of it. So if we wanted to keep going, it's just going to be downwards, or sorry, upwards, and then you have a downwards. Over here we would have the downward, and then we'd have the upward part. So again, if you know the part between 0 and 2 pi, you can do the rest of it. All right, cosecant, that's cosecant. Secant will be very similar, it's just cosine. So if we're going to graph the function y equals the secant of x, just remember secant is 1 over cosine of x. So let's go through, compute some cosine values. So cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi is a negative 1, 3 pi over 2 is going to be 0, and 2 pi is 1 again. So 1 divided by each of those. So 1 divided by 1 is 1. 1 divided by 0 is undefined. Then we get a negative 1, undefined again, and a positive 1. So I can plot points at x is 0, y is 1. So 0, 1. At pi and negative 1, so pi is negative 1, and then at 2 pi and positive 1. So we actually get 3 points this time. And I get asymptotes at pi over 2 and 3 pi over 2. So pi over 2 and 3 pi over 2. And if you remember, again, our period normally is from 0 to 2 pi. It's still going to be that here. And again, same thing, as the normal cosine graph curves down and gets smaller, the reciprocal of that means it has to get bigger. So it's going to go up, and then it's going to go down, and then it's going to go up again. So secant graph actually has 3 parts, although the 2 parts on the top, when you kind of mirror each other, they're going to keep going together. So this is the 1 period graph for secant. And again, if we kept going here, this graph would curve upwards, and then you'd have 1 curving down, and then you're going to have this graph continues up, and this one continues down. So we have vertical asymptotes everywhere that cosine hits the x-axis. And we had the same thing happen with sine. Every time sine hit the x-axis, you had a vertical asymptote. And then you're just going to draw sort of the same graph but mirrored away from itself. So we get, again, this is our standard graph here. Okay, so let's just summarize what we've seen for secant and cosecant. Both of them have a standard period of standard period length of 2 pi, which is just like normal for sine and cosine, and it goes from 0 to 2 pi. Cosecant will be undefined at every pi. Okay, so cosine is undefined at all multiples of pi. So that, 0, 1 pi, 2 pi, 3 pi, 4 pi, negative 1 pi, negative 2 pi. And then secant will be at the odd pi over 2's again. Okay, so it's undefined at all the odds. So it would be defined at like 2 pi over 2, which is just pi. And again, this first statement for each one, cosecant of x plus or minus 2 pi is equal to the cosine of x. That, again, that's just saying if you shifted the graph a length of the period, so 2 pi, either left or right, and you can actually do a multiple of that, but it's just a carbon copy. It's just copying itself to the left and to the right. And so it's going to do that forever. All right, the last one we need to look at here is cotangent. And again, we're going to follow the same process here. We know f of x is going to be cotangent of x. And we're going to think in cotangent as in terms of cosine over sine. So let's run through it. Again, we have some chosen values for x. So sine of 0 is 0. Sine of pi over 4 is root 2 over 2. Sine of pi over 2 is 1. 3 pi over 4 is root 2 over 2 again, and then pi is 0. Cosine of 0 is 1. Cosine of pi over 4 is root 2 over 2. Cosine of pi over 2 is 0. Cosine of 3 pi over 4 is going to be a negative root 2 over 2 because it's the x coordinate, and cosine of pi is a negative 1. All right, for cotangent, we're doing cosine over sine. So 1 over 0 is undefined, so we're going to have a vertical asymptote. Root 2 over 2 divided by itself is 1. 0 over 1 is 0. Root 2 over 2 divided by itself with a negative is going to be a negative 1. And then we're going to be undefined again at the end. So we're going to have a vertical asymptote at 0 and at pi. At pi over 4, it is going to be at 1. At pi over 2, it's going to be at 0. And at 3 pi over 4, it's going to be at negative 1. And so if we just kind of continued the curve through the points, it's got to come off the asymptote, it's got to pass through our points, and then go towards the asymptote again. So it's going to look something kind of like that, which is similar to what we saw with tangent. Tangent started over here at a negative pi over 2, and it was an increasing function. So it went up. So cotangent's a decreasing function, and it's between 0 and pi. Now, notice that it still does actually have a period of pi, just like tangent did, but it's starting at a different location. So it's going from 0 to pi instead of from a negative pi over 2 to positive pi over 2. So that's the one period. That's the one cycle of the graph. Everything else is just going to be a repetition of that. So again, we could draw more parts to this graph. It's just a matter of copying it over and redrawing it. So we're going to have another asymptote here. And so again, it's the same thing. Okay, so that's what cotangent would look like. And again, just to summarize cotangent, again, once you have the graph of cotangent, you can move left or right by a distance of pi, because its period is pi. We're going to say our standard period is from 0 to pi. Remember, sine and cosine, secant and cosecant go from 0 to 2 pi. Tangent goes from negative pi over 2 to positive pi over 2. So cotangent goes from 0 to pi. So it's a little different. And it will be undefined at all the multiples